right, welcome back. So to the very last lecture of this seminar. This semester is a different one, is a unique one, is an interesting one, and we've done everything online. And then we will actually skip the base part, Bayesian warm-up part, because we will have a summary, very overall summary at the very end. So today I will just jump into the topic that I prepared. So we've talked about a lot of modeling instead. We talked about coin flipping, the globe example, the regression, linear regression, the risk-Lavagna, and the counterfactual double update risk-Lavagna, and we talk about hierarchical modeling. Okay, that's what we have seen so far, and we coded quite a lot of stuff in Stan. But I guess you're smart enough and you realize that Stan is not a language. It's not like R, we could select one line and then execute it. We cannot run that line. So we could only code an entire Stan script and then run it. And then if we see error, we go back to the Stan file and then we try to debug it. So this is the kind of the challenge, because it seems like a black box. It seems like it requires you to know a lot of Stan so that you could correctly code whatever you want, distribution, variable name, okay? So Stan is, to most of us, a new language, and the language feature is also unique. And that's what we have seen. So today, the big topic is that I list a few common mistakes when we code in the Stan language. So to try to minimize the error and the mistake as much as possible. So if you have this common mistakes in mind, you could basically avoid it when you are doing that. And then if you are already doing everything correctly, and if you still see some errors and some warnings, then that might be challenging. And then you can ask me, okay? So today we just talk about some common mistakes, the Stan debugging. Good. So before we really go to the debugging part, so let's talk about the style tip a little bit. So this doesn't really apply to Stan only. It is an entire good programming practice. Whatever you use, R, Python, blah, blah, Julia, MATLAB, everything, Java. So whatever you do, whatever you use, so make it reproducible. So that's why that we want to make a lot of comments in the script, so that you could remind your future self what you have done. You might be very clear at this moment what you are doing, but maybe 2 days later and after vacation you come back from the mountains, from the beach, you really can't really recall too much about what you have done, and you lost that momentum when you were doing that. But if you make meaningful informative variable names, and then that really is a hint so that you know what you have done before. Good. So scripts, they are good, always good documentation. Say we are seed. The seed is for the random number generation. So whenever we use the same random number generation seed, we will always get the same results. So this is for reproducibility. So here I wrote in the comment that not across platform, what I mean. So if I use the same seed in R and you use the same seed in R, we will get exactly the same results. But if I use the seed in Stan and you use my seed in Stan, we will pretty much get different results, because the compiling part, the compiling from Stan to C++ requires some of the hardware of your computer, because my hardware is different than your hardware, and then that's why we cannot get exactly the same results. Okay, this is only something to keep in mind. But as long as you use the seed on your own computer 1 time or twice or 3 times, as long as that's your computer, you will always get the same results. It is guaranteed. Okay, by the way, today the talk will be a little bit technical, so if you have no idea what I'm talking, this is totally fine, okay? And second is make it readable to give meaningful and consistent variable names. So instead of calling the number of participants capital N, we could say number of participants, N sub J, something like that. So that's more informative than using capital N, right? Give meaningful variable names, yes, I said that, and start with simulated data. And a lot of times, we recruit data from participants, and we all know that in real experimental life, the data can be quite different than what than an ideal environment, than an ideal setup. So how about we create an ideal setup in the first place by using our domain knowledge to simulate some data? So we know that all of the models, regression models, learning models, they are generative tools. Generative means we could use the model to generate data. So it assumes a generative data generating process. In the learning example, the risk-Lavagna is trying to assume the choices are generated from a value computation, right? And we use the basis. We could select arbitrarily a learning rate, for instance, and then we could simulate choice data. And then when we have the choice data, we could fit the model to the simulated data, and then to see if everything's working well. And this can be done even before you start your data collection, and to make everything very sure that it works, and then you can go ahead and then you can click on your clock, so then you could start your actual data collection. Another tip, what I think is very important or useful is that design top-down and code bottom-up. So this means you might really come up with a very complicated model. And even though you have a very complicated or complex model in your mind, do not start with that complex one. You start with the simpler version. Simpler version means, well, you have a complex model, but the complexity doesn't from out of blue. The complexity comes from some basis, some core parts. Say, I'm not sure if you have read my preprint. So that one is that the model is a little bit complex, but the core part is basically the counterfactual double update model we covered from the last week. So basically what I did is I started only with the simpler one. So this counterfactual double updates, because there is the social component, but in the first place, we didn't really pay attention to the social component. We just focused on the direct learning part. And then later we gradually built piece by piece, some complexity on top of the simpler one. So the advantage of doing this way is that if the simpler version works as you expected, if something happens incorrectly in the future version, in the more complex version, you are sure that the additional complexity is the place that causes the error, causes the problem. And everything before that, the simpler version, they're fine, they're totally fine. And as opposed to if you code in the first place a very complex machine and complex engine, and if you have an error, you really have no idea where is the incorrect part. It might be the simpler part that is wrong, or it might be other reasons, the more complex parts that are wrong. So you have no idea. So that's why I suggest design top-down. You have a big picture, what might be the most complicated model in your case. But when you are really doing that in the implementation level, do it bottom up. Start with simple and then gradually make it a little bit more complex, okay? The last one is write comments, but I said this already, to do a favor to your future self. Anything else? Yeah, code never lies, yes. This actually happens to me quite often when I was doing that earlier, in the sense that if I want to change the code, I change the code, of course, but sometimes I forgot to change the comments. So the comments stay the same as before, but I adapted the code already to something new. And to make it consistent, if you change the code, also updates the comments, okay? Even though code never lies. And if you see there's a mismatch between the comment and the code, trust your code, right? Do not trust your comments. The next small topic is the editor of coding. The editor, excuse me. The editor here doesn't mean the editor of the journal. So the editor here means the software. Which program that is more favored when you are doing coding, for example. And so we used R so far, RStudio, and we see the nice syntax highlighting. So we see here the block name, data parameters, and model, they're highlighted. Here the data type for integer and for continuous. And then this one, the distribution name, they're also highlighted. And there's something called Notepad++. This is a pure text editor, and you can also use text. And then there are two others. One is called Sublime, the other one is called Atom. Atom is also actually from GitHub. Both of them here, these two, I mean. So both of them, they also have the syntax highlighting feature. And at least all of them for a reason. So because previously RStudio didn't really have a good support to the Stan language. So when I started, I used the Sublime a lot, and then I also tried this one from time to time. And because these two, they have sometimes nicer editing feature. And we don't have time to cover that, but if you read their manuals or documents, you can see they do have some advantages over all the other text editors. But anyway, from maybe 2 years ago, RStudio started to have a really unbeatable support to the Stan language. So I think nowadays people use this one a lot. And we also use this one a lot in our course. So to keep it short, use RStudio is enough. And if you do not have a strong favor to all of the others, then just use RStudio. Good. So now we could go to the summary, the list of common mistakes, common errors, and common warnings. So when we run a Stan model, if we run it, and we could have 3 outcomes. One is everything is smooth, and we run it, we get a result. No complaint from the computer software. The second outcome is that we get an error. So error means something is wrong, and then the program had to be stopped. Okay, and then the error message is returned, it's shown on the console, and then we can see what the error message are. And in the first place, the error messages, they could be a little bit overwhelming because you didn't really know what that means, and that's why I'm telling you what that means. So the third outcome is a warning message. So warning basically means everything runs okay, but something might be not as ideal as a perfect case. Something is not so perfect, even though that doesn't really impact the model run smoothly. Okay, the model might still run smoothly. You can still get the MCMC result, but then there is some complaint, and that's the warning. In this case, you will still get the results. Okay. So if you receive an error, you will never get the results. Something's wrong, the programming will be stopped. And if you get a warning, it will not be stopped. You will get the results, but sometimes the result is not trustworthy, is not reliable. So I will tell you why a little bit. Okay, good. First of all, the errors. The most common one is basically we forgot the semicolon. If we write some lines, each line, they have to be terminated by a semicolon. And if you forget this, you will get an error for sure. The second is misindexing, so mismatch or constants. So for example, if you have a vector which has 10 elements, and you are trying to access the 11th element. So this is not possible. So this is mismatch, right? And then support mismatch. So this basically, support basically means, well, whenever we want to use a variable, as I said, we have to declare the type, declare the data type in the first place, and then we use it. So support basically means it checks if the declaration and then the place where you use it, they are consistent. So to give you an example, if you declare a variable as an integer, and then later you assign 1.1 to that variable, 1.1 is a continuous, so then there's a mismatch. You cannot make a integer you previously declared as a continuous variable. So this won't work. You will, of course, also receive an error if you do that. And you will actually realize that, I think. The second one is a little bit difficult to realize, because if you do not go into the loop, you will never see the model is trying to access the 11th element of a 10-element vector. The fourth one is improper constrain. So then that basically means the lower and upper thing of the model. So if your data, for example, the range, if you have twice data, you have 1, 2, choosing A and B, as we have seen. But let's say you have -1 for missing trials. And then in this case, when you are trying to declare the data variable in the model, in the model script, in the data block, you cannot say lower 1, upper 2, because lower is -1, including the missing trial. So two possibilities. One is to keep the missing trials, keep it there, and then you say in the data block lower is -1. This is one possibility. Another possibility is to remove all those missing trials beforehand, so that the actual data you give from R to stem only contains 1 and +1 and +2. So lower 1, upper 2 in this case. An improper dimension declaration, that basically means the dimension is mismatched. And the next one is vectorizing when not supported. So we said vectorizing is a good feature of the STEM language, and we could always try to do vectorizing as much as possible whenever we can. And whenever we see a loop, we could think about if we could get rid of the loop by utilizing the vectorizing. And instead, even though this is recommended, but sometimes in particular cases, vectorizing is not supported. So vectorizing is not 100% sure accepted. So if you are trying to vectorize something that is not supported, you will also get an error. And in this particular case, the error message will actually tell you or educate you what can be vectorized and what cannot be vectorized. And then you just find out where that is unsupported in your model. Wrong data type, this also relates to the integer and the real thing, I think. And the wrong distribution name. And then this one refers to typo, it refers to typo. But then the typo doesn't really only apply to distribution name. The typo can happen everywhere, right? When you were declaring variables, when you were trying to write the models, avoid typo, right? But whenever you really have a typo, you will also get an error. Forget priors. This is a little bit difficult to say, because most of the time, if you forget to declare the prior, you will not get an error, but you will get some improper model behavior. So I will tell you later. So if we do not give a prior, by default, the parameter will be sampled from a -2 to +2 range for 100 times. And if this initial sampling worked, then the model could continue. But if this is the initial sampling without the prior for 100 times sampling doesn't really give a reasonable fine-tuning internal running algorithm, then the model will stop. You will get an error. So what I refer to is in this case. So forgetting the prior doesn't really always give you the error, but it depends. But as a rule of thumb, just always give priors, right? Whatever the consequences are, you just give priors. The only exception that we could tolerate is that if we have a uniform prior, and as we said, uniform prior doesn't really make too much sense, and we do not have to write it spelled out explicitly in the model block. Yes, it is correct. So if we have a uniform prior, we don't really write it. But if we have other priors, normal, unit normal, standard normal, there's nothing called unit normal, sorry, a standard normal distribution, we just have to write it. Last one, misspelling, typo, okay? Any questions here before we go to the warning part? There is a question, if we do not have any priors, we should still add a flat prior, right? It depends. It depends on the range of the parameter. If you have a parameter that has both ends, lower and upper bounds, in this case, if you do not write explicitly, this by default will be a flat prior, yes? But if you have a parameter that doesn't have a constraint, so it can be from negative infinity to positive infinity, you can't write a flat prior for that, right? There is no uniform distribution from negative infinity to positive infinity. So in this case, you need to have a proper other prior. It can be a very wide normal distribution. You can say, well, normal mean is 0, standard deviation 10,000. This is flat enough, I think, in this purpose. Other questions? Okay, so if not, we go to the warning part. The warning part actually, we have seen most of them. So the error part, because I'm showing you what should be done correctly, and we rarely see errors in our class during the exercise, but we do see warnings, and some of the warnings I show you on purpose because I wanted to show you what is inappropriate and why we receive a warning and how to avoid the warning. For example, when we were discussing the reparameterization as a way to optimize the model, optimize our hierarchical model, the very first attempts of the hierarchical model, we did receive quite a lot of warnings. And then after the optimization, we got rid of all the warnings, and auto sampling, they work very fine. And the chains, the MC-MC chains, they mix pretty well. Good, so the warnings. The most common one is forget the last blank line, and this is harmless. And nowadays, the RStudio software, when you are trying to code a STEM model, it actually forces you to really add a last blank line. That actually means you cannot delete the last blank line. This is the harmless. If you don't have it, totally fine. Some other warnings can be that your current STEM version might be 2.18, 2.19. But if you have using STEM for quite some time, your coding style might be coming from 2.15. So some of my old scripts, the way I'm coding is actually from a little bit older version of STEM. So if I use a newer version of STEM, which runs an older version of the code, I will receive a warning. And then the warning basically says, well, some of them, they will be discontinuous in the future release, and try to avoid it and try to replace something with something else. Something else here refers to the newer way to code it, okay? this won't be a problem for you, I think. Okay, numeric problems. Numeric problems refer to two instances. One instance is 1/0. So we know that if we do a division, 0 cannot be the denominator. So we cannot divide anything by 0. So 1/0, 2/0, this is not possible, this is not accepted. And if this happens in your model, and then you will also get a warning, okay? Another instance is the logarithm. Log 0 also doesn't exist, okay? So log 0 basically results in a negative infinity, and then this we cannot do it. The SNAP model cannot deal with that. So to summarize, 0 cannot be the denominator, so 0 cannot be the input of the log function. Why this is a warning? So it is because if we have a parameter called alpha, for example, and if we say 1/alpha, and if the range, the legal range of alpha is between -1 and +1, it in theory can be 0, but because this is a sampling procedure, maybe once or twice over out of the 4,000 samples, alpha is 0, but all the other 3,998 times, alpha is not 0. You are fine. So only 2 out of 4,000 times you will get this numerical problem, numerical warning. It is of course not accepted. So Stan will tell you 1/0 is something that we do not accept, but this is not a problem because the sampling thing, it goes here and there. Occasionally it is not allowed, fine, this is totally fine, good. In other scenarios, if the entire 4,000 sampling, you always get this 1/0 problem, then this is problem. This might be a mistake. So then this might be an error instead of a warning. So these are two scenarios. To make it short, if this numeric problem happens very occasionally, you can ignore it. And if this happens all the time, you have to fix it. Okay, this is the suggestion. Last one, divergent transitions. We've seen many times. So if we have 4,000 times of sampling, and if some of the chains, some of the samples, they do not really converge with the majority part of the sample, you will see divergent transitions. So actually the divergent transition is a little bit difficult to understand, honestly, in the stand sense, but you can just basically imagine that some of the samples, they are off. They are a little bit away from the majority of the samples. If we see divergent transitions, what we do, okay? But before I tell you what I do, I summarize all the other warnings because they're related. The second common warning is this one. So the maximum tree depth is also a Stan internal sampling algorithm. If you still remember, the default value is 10. If that hits the maximum, then that means 10 is not big enough. And if you want to deal with that, then you do have to increase the maximum tree depth from 10 to 20, for example. And this one, the BFMI, is something like Bayesian fraction something information. It's low. This is also a warning message. And then the next one is improper prior. Okay, so these three, divergent transitions, maximum tree depth, and the Bayesian fraction information too low. So how do you deal with that? So this is indication. So all of these three, they are indications of optimization. So if you see these three warning messages, you might have to go back to your model to see where it can be optimized. So if you see these three warning messages, it doesn't really mean the model is wrong. So if you just translating some model in the paper to the Stan language, the model worked well in the paper. Why does not it work here in your case? So it doesn't really make sense. So if you see these 3 warning messages, this doesn't mean the model is wrong. So what it means is that maybe the model is a little bit numerically difficult to sample from. So you will have to reparameterize to make, so this is the original model, let's say, and you have to make a reparameterized model to optimize the original model so that this optimized reparameterized model and the original model, they are equivalent, right? We always say we'll use the standard normal distribution and to optimize the model. But in fact, with optimization and without optimization, they are equivalent, they are the same thing. So the model is not changed. What is changed is the way to sample for STAN. So make an equivalent model to make it more optimized, to make it reparameterized, and then this one, usually you will see no more warning messages after these procedures. So however, this is not a guarantee, right? If you do every optimization, if you do every reparameterization, and if you still see all these warning messages, what do you do? So this one, you will have to change the STAN internal sampling parameters. Examples are the number of samples. Instead of 2,000 per chain, you can say, well, 4,000. Instead of using 4 chains in parallel, you can say, maybe I need even more, maybe 8 chains in parallel. And we could also change the acceptance rate, the MCMC acceptance rate, the how it's called, adapt delta. That one by default 0.8. You can also change it to 0.9, 0.95. And the tree depth from 10 to 20. And then there's a step size. So how large the sampler, remember the MCMC robots, how far the MCMC robot travels from one location to the next. And you might want to make the step a little bit smaller so that each sample is more fine graded relative to the step size is large. And if you do all of this, I guess you will have a proper model estimate. And if you forgot what I said, if you didn't really catch what I said, this adapt delta, this tree depth, and this step size thing, so go back to the slides maybe 2 weeks ago or 3. So when we were trying to cover the topic of optimization, I talked about the meanings of all these parameters, and I also talked about how to implement them when calling from STAN. Good. And improper prior, so this one, I'll give you an example. So actually related to the question Jakob asked, so if we have a parameter that doesn't have a range, so we have a parameter from negative infinity to positive infinity, and if we were really trying to give a prior, for example, uniform prior, flat prior from minus 100 to positive 100, even though this sounds large, but there is a range, it is a mismatch relative to the originally unbounded parameter. So this is improper, and you will actually also receive, maybe not an error, I'm not really sure, but you will definitely receive a warning because it doesn't match, right? They do not match up. Good. Questions so far? All right. If we do not have questions, let's go forward. Some practical advice. So debugging in STAN, so how do we do it if we really try to make it live? And if we code our own model, and what are the practical tips or practical advices that I can give you? So first of all, always write a STAN file. So we save something as a .stan file. So this is our model. This is actually relevant because previously, when the Stan language was first invented, some of the people, they write a long text, a character, a string variable in R. So A equals, in quotes, inside there's a Stan model. And I really have no idea how those people, they debug the Stan file and the Stan model. Don't do it, so just use a Stan file. It's actually still common that some people, they write a huge character variable and to treat it as a Stan file. I don't get it. Anyway, we use a Stan file. In our studio, so this one I showed you earlier. So if we are working on the if we are working on a Stan file, if we are working on the Stan file in our studio, so in the Stan file, up the top corner, top right corner, there is a check button in RStudio, I mean. So this one checks the syntactical correctness of your model. So basically check the grammar of your Stan model, like grammar check. Always, so when you are finishing a Stan model in RStudio, always press the check button before you move forward. And the check button basically tells you where is grammatically mistake. And a very useful function is called lookup. So what is a lookup? Let's say you are an expert in R already, and let's say you really know a lot of the function names in R, but you have no idea how this function is called in Stan. This is possible, right? You know R, and you heard from colleagues, hey, let's use Stan, and okay, good. And you know a lot of R functions, but you don't know how those functions are called in Stan. And luckily, there's a function provided by the Stan team. The function is called lookup. Suppose that we know the probability density function of normal distribution, so the PDF of a normal distribution in R. This is d norm, right? As we learned, d norm for the density of a normal distribution. And we would like to know how the Stan language is calling a density, normal density distribution in the Stan language. So if we say, well, we want to look it up this one, so the results are here. So this one is normal, is the name of the distribution that we have seen many, many times. And then this one is to calculate the log of the normal, of the density, and also takes different input arguments. And then this one is actually from the old output. Nowadays, if you say look up d normal, you will see this one, of course, but this one is replaced. And I think I need to change this. This one nowadays is LPDF, log probability density function, instead of calling it log, okay? Good. And then the fourth one, I told you already, start with simulated data. You have a ground truth. You know what is correct, and then you simulate data, and you feed the model to the simulated data, and then you see if the model is correct. This is also the debugging. And the last tip is be careful with copy-paste. So always be careful with copy-paste when you are programming. That's good when you are doing programming. And particularly because if we want to record the log likelihood variable, we have to use the generated quantity block at the very end, if you recall what I'm saying. And how to do this log likelihood recording part, what we did is we literally copied from the actual core part from the model block down to the generated quantity block. And we replace the sampling statement with a log likelihood calculation. So that is the only change. And if you remember that, and you see here, this is the most common copy-paste when you are trying to do everything in Stan. Good. So be a little bit more careful, right? Because you're copy-pasting, and then double check if everything is fine, and if you change the dimension of some variables, it's possible, and then to make it more consistent. Good. And the last one, this is actually my favorite tip. we want to, if we have a model, if we have some data, we want to feed the model to the data, we want to get it run, we want to get the results, and we want to get the figures, and we read about it, and we publish it. This is ideal case, right? This never happened so smoothly. So if you run 4 chains with 2,000 samples per chain, and if something gets wrong, and then it gets wrong, right? So usually the tip here is that instead of running 2,000 samples per chain and 4 chains, you could actually run 1 chain, 1 sample. So the rationale here is that if 1 chain and 1 sample, even though that doesn't make sense, if that runs through, it runs from the beginning to the end, usually that doesn't really take too long, right? As long as that runs from the beginning to the end for 1 chain, it shouldn't have a problem if you run multiple chains, multiple samples. So this is what I do. I have usually code a function and which have a flag. So this flag tells me if I want to do a test mode or not. If I do test, I do 1 chain, 1 sample, and if this test is false, and then it will run 2,000 samples and 4 chains by default. I can also change that, but this is the untest mode. This is a very good practice, I think. I really encourage everyone to do that if you want to do it in the future. I also recommend my colleagues if they are using Stan, and I recommend them doing this way. Great. Debugging by printing. So this is the last tip. So if you code in Python a lot, you print a lot, I think. So print here also works in Stan. So for example, this particular line, if we want to know where am I now, which participant I'm running, which trial I am running, so what is the value so far in this particular person in this particular trial? The value is the whatever value, risk-Lavagna value. So the printing, it works this way. So this one automatically does a converting in the sense that as here is an integer, it will be converted to a character, a string. This one will also be converted to a string, and then this one will also convert it to a string. Another important feature is this line has to be terminated by semicolon as well. And this one, in the beginning, I didn't know that. I was trying to print everything, and I was like, why this doesn't work? And then I realized that, okay, this one also requires a semicolon. So basically, whenever you do coding in Stan, just terminate every line in semicolon. Not every, so here you don't have to do it in the curly brackets. Here you don't have to do it, but everything inside of curly bracket, you have to use semicolon. Good. Questions? Okay, if you don't, I don't know if you have. Let's say you don't, don't see pressing questions. So here, this is an extremely simple example, data block, the W and N in our earlier example. And this one, the unknown parameter theta, the proportion of water covering the entire Earth. This is the check button. And if we code the model, we always press the check button to check if everything is syntactically correct. Good. And then the check button actually is equivalent to this function, but usually we do not have to write this way. Good. And for this educational purpose, I will show you a exercise, but I will do it, and you just basically watch. And when you are watching, think about why am I doing that? Okay, so this is the exercise. So let's say there is a memory retention task. So memory retention task basically here means, well, there are 3 participants, and then they have to memorize a list of words, a list of items, chair, table, banana, cucumber, whatever. So they have to memorize items. There are in total 18 items they have to remember. So they first remember, and then afterwards they do a free recall, for example. So they report what they have memorized, and then they tell the experimenter, chair, table, blah, blah, until they cannot name even further. As you could imagine, immediately after the memorizing, they can report nearly every items on the list. And then the participants, they were also tested after maybe 2 hours, 4 hours, 7 hours, 12 hours, or maybe days, doesn't matter. So basically at a future time points. So they were asked to record items again and again. And you see that in the beginning, the participants, this one, for example, the first one could report all of the 18 items. And also at the second time interval, the person also could successfully recall every item. And then later, 2 cannot be memorized, cannot be recalled. And then here, 3 cannot be recalled. And then this one, the item that can be memorized or can be recalled, getting less and less, okay? From 18 here to drop to 4 after 99 time unit, whatever that is. And then if you plot it, you'll see, well, these 3 colors, participants number 1, 2, and 3, so they follow kind of a exponential decay. So this is something we know quite often in the literature. So this is exponential decay phenomenon in the memory domain. And we just want to model this curve. So why there is this decay and what can be captured by a computational model. Okay, good, short introduction. And what is the model that we can use? Well, I told you already, exponential decay and how to do it. So there is a key parameter which is called the recall rate, the probability to recall an item. So how likely the person can recall a particular item, probability of recall or probability of memorizing, right? So doesn't matter how you call it. So this probability of memorizing is calculated in this way. It takes the minimum, it takes the lowest number between this one and this one. So this is 1, right? 100%, and then this is the exponential decay part. So if this term is above 1, the minimum of this 2 is 1. So this means 100% memorizing, no forget. And if this term is smaller than 1.0, the minimum between these 2 is basically this term, and depends on how large this term, this describes the rate, the probability of memorizing. For example, if this calculation resulted in 0.9, then that basically means 90% probability this item will be memorized, and 10% probability this item will be forgotten. Okay, this is the exponential one. And then the exponential one takes 2 parameters. The beta here is like the intercept, like a regression model. You could imagine that this is A multiplied with X plus B, alpha multiplied with X times B, plus B. This is the intercept, the same idea as we have seen in regression models. And then this one, this is not a alpha times X. So this is alpha times X, take the minus, and then take the exponents. The T here basically means the time unit. We give 1, 2, 3, 99. So the time unit is on the x-axis. The exact data, this is the data we give. This is exponential decay, and when we know that, what is, wait, I have the meaning here, okay. So when we have the exponential decay, what do we use? What distribution do we use? So think about it for 1 minute. What is the distribution that we can use for this particular case? So we have a probability, we have a total number of items, 18. And each time the person is reporting something in between 0 and 18. Does it sound similar to an example? We have 9 times of experiments, 6 times of water, or maybe 5, doesn't matter. And there is one parameter. This is the proportional probability. Right, that sounds similar, right? Yes, so if you are following my thinking, we will use a binomial distribution for this particular case. Good. Anyway, we go to this exercise. I will do it for you. So there is a main R file, and then there is a stand file, and we will try to debug all of them. And then I prepared a lot, and at least 9. So why I say could be larger than 9, it's because if you are doing this exercise, you might change something from correct to incorrect. And then in this particular case, you will have more errors. Good. Give me a second for getting the files. Let me know if you have questions so far. Have a stretch break, water break. Can you see my screen sharing? They are studio in this case. Can you see my studio, all of you? Yeah, okay, good. Okay, so we have a STEM model and seems complete, okay? Data block, computer block, and transformed parameters block, model block, and generated quantities block. Great. What do we do first? First place, always check. Yeah, we get an error, good. This is easy. So there's a semicolon forgotten. Wait, let me save it as something else because I want to keep this original mistaken file. The size. And then the nice thing is that it actually tells you which line it is expecting a semicolon. So here is around 12 or 26. And then here there's also a red cross sign that tells you this might be wrong. So go here and complete the semicolon. So basically you are trying to iterating this process by repeating the check, debug, and check, debug process. We fix one, and then we have to check again to see if everything else is okay. Good. And of course, there's a new one, right? So this is actually a little bit difficult. So what is that? I guess, sorry, I was trying to ask you to think, but this one is not so obvious. This one, so what you see here is actually that you have this one. You do have to know it. Otherwise, this is quite difficult to find out. So in the we are used to the case where we give a lower bound and upper bound to the variable that we declare. However, in the model block, we cannot do this. Okay, in the model block, we cannot give explicit lower bound and upper bound to a variable. So we have to delete or remove this variable, this boundary declaration. And then if you read the error message, it actually tells you this in an unclear way. So in the model block, it requires undefined. So undefined is true, means I want it to be undefined. Undefined means no lower and upper bound. But what's the model found when I was trying to check the syntactical correctness is it found identifier. Identifier means here lower and upper bound. So basically, it doesn't allow identified, but it founds identified. So this is a mistake. You see what I mean, right? So to simply explain is basically we cannot give a lower bound and upper bound in the model block. Remember this, and if you do it, you will see error. And then error message is a little bit unclear to understand. Good. So we fixed that, and then we could move forward, and then we will see something else. And then we see something around here. This is okay. So let's see. So in this case, what you see is you go to the model, and you go to the line where it refers to, and then try to find out where is correct and where is incorrect. Okay, good. So there are a few things that I have to mention this line, because this line is quite important. This is the core part of the exponential decay. So take the minimum between 1.0 and the exponential term. First of all, this F min is not a mistake. It is a preferred way to obtain the minimum. So if you read in the STEM manual, it tells you actually that min, min, that function is not preferred. Instead, it prefers to use a f min. So this one, don't change it. This is correct. Taking the minimum between 1.0, 1.0, nothing wrong here, right? This is okay. And something might be wrong here. Good. And then this line is has two problems. So one is that you see we are trying to do a hierarchical model. Hierarchical model means we have the parameters for both individual level and for the group level. And at the individual level, that means each person, they will have their own beta, and then they will have their own alpha. Good. And then the alpha and the beta, if you go a little bit upper, you will see both of them, they have a range. So both of them, they are vectors, and both of them, they have elements of the number of participants. In this case, 3, okay, good. This line is a calculation, and then this one is actually, this one should be a integer. However, beta, if we write only the name, it is a vector, and it doesn't really reflect the nature that we are trying to use a individual level beta. The explanation is a little bit complicated, but basically that means we want the beta per person. So then we have to give the participants index. That's it. Good. Another thing is actually, well, alpha, we want to do the same. However, this is a silly typo. So instead of doing S, I wrote NS. This will not be error. If you run everything, you will not receive any problem, assuming we only have this error. But this doesn't make sense. So this means for all of the participants, they will use the parameter from the last person, because NS is a constant. In this case, 3, but if you have 100 participants, NS means 100. So this is a silly constant indexing problem. It's subtle, and you do have to be very careful to pick it up. Okay, good. S, not capital, small s. Good, good. So there are something else. And actually we see from here this red cross, and we do not have to really change, press the check button. So what that means, so here again, we can read the error message. So I don't know if you can see at the very bottom, the last two lines, it says too many indices. Expression dimension is 0. However, the indices found is 1. So what that means? In the stand term, dimension of 0 means a scalar. Dimension of 1 means a vector, and dimension of 2 means a matrix. So here, that basically means it should be a scalar. However, what it found is a vector, the interval of t. What is interval? Is the task variable is 1, 2, 3, the time intervals. And we know that the interval, there are multiple inputs, multiple instances. So this might be something wrong in the data block. So we have to go up and up. We see here, this is the place where we declare interval. And for some reason, I forgot to give the size of the intervals. So then you have to give the size of the interval. All right, check again. And now we have something else. Okay, good. So this one we see an item, and that basically means if you read the message and it tells you that this one is not found. So an item is the number of items, number of the items you have to remember, chair table, that's 18. This is declared in the data block, so go here. And if you are careful, and you will actually see that this an item is not the same as this an item. So one is a smaller case of I, and then the other one is a capital case of I. Good. So what you have to do is to make it consistent. And then there are two possibilities. You can change both of them to be capital I and items. You can change both of them to be smaller case I. And there are two possibilities, right? And what do you do? How can I know what is the correct one? Do I make it arbitrarily? If I like capital case, then I make capital case. If I like small case, I make small case. No, you do not have freedom here. You really do not have a freedom, because the data block, they have to be the same as in the place where we give the variable name in R. So here, if you go here, here in this case, that's the data list that we will parse from R to stand. And then in this place, we have a capital I. Okay, so by the way, this name, you have freedom to make it whatever you like, small or capital. But as long as this one is decided in the stand file, they have to be consistent. All right, so capital I. There's a question, what is dimensional 4? Hypercube, I don't know, maybe. So let's see here. We have a new error message. So it tells you that this found binomial is okay, the binomial distribution, and then the int with a comma in the square brackets. This one also suggests a two-dimensional variable. This actually means a two-dimensional array. So what it tries to tell you is that this one is not accepted, and it then later tells you what are accepted. In this case, this is a scalar, this is a vector or one-dimensional array, but it doesn't support two-dimensional array. Good. But if you know the task, what is missing here is, well, we were trying to model the number of record items per person per trial. So what is missing is actually the participant and trial index. So here I'm suggesting two ways of debugging. So one way is to check and debug, check and debug requires you to know a little bit the programming language, okay? This is one way to debug. Another way to debug is that you are the person who is running the experiments and you know the knowledge, you have the knowledge of the experiments. And so you use your domain knowledge to debug. This also helps. So we know that here in this case, we want to model the record items per person per trial. So if we put K here, only K, doesn't make sense. We have to put the participant number, trial numbers, trial index. So to summarize, the debugging goes both ways. One is from the code itself, only from the code, only from the programming part. The other one is from the knowledge of your experiments. And if you do both ways, then you will find out the errors and then you will fix them. Good. Check more. Right. Let's see. So if you see here, this one, the parameters alpha and beta, this is a mistaken variable. So both of the parameters, they are real numbers. Okay? And then if you read the message, you can actually also find out. Well, go ahead. Yes, so now we see that. So this model is syntactically correct. So there is a warning message here. So this actually suggests the one I told you, the older version. So what I did is to use a hash tag to do the comment. It was supported earlier, but for the most recent version of Stan, it uses // okay? So this is a warning message. This is also harmless. This is fine. And then we click again, and then we see the nice syntactical correctly message that we would expect. Okay. So I have a quick summarize. So we are trying to debug, and then debug always starts from checking the syntactical correctness of the model. And then if you check, and then if you fix error, check again to find if you have further error messages. And do this until, iteratively, until you see this finalized nice line to tell you everything's fine, and then you can go forward, calling the R Stan model from R and do the sampling. Great. So we are not done here yet because I was creating all those mistakes, and even though you see this, you do have to be a little bit more careful. So what I told you earlier, something is not so easy to pick up is the prior. So my own practice is that whatever you declare in the parameters block, okay, whatever you declare in the parameters block, you will find the counterpart. You will have to find it in the model block. So if you highlight this variable, you see, can you see here also the highlighting, the frame? If you see that, then that means the prior is given. If you highlight the second variable, and you see this is also prior given, okay? Only exception is I told you the lower and upper bound flat prior. That is fine. We do not have to find the repeatedness, the repetition in the model block. But all the other cases, we do have to find the repetition in the model block. So this one, if we go down, right? So here we don't see the prior. So we have to give it. So what is the prior? What is the parameter? You have to ask yourself. So this is the hierarchical model. So we are using the standard deviation of that hierarchical model. First of all, so those hierarchical standard deviation, they have to be above 0, right? Standard deviation by definition, they have to be positive. Okay, good. And for the second standard deviation, we have to do it again. I'm copy pasting, but here it's harmless to copy and paste. And we haven't fixed that, right? If we do this, we cannot find the repetition of it. Well, then you have to do it. For the standard deviation, if you recall from our lectures, what we have been using is the half Cauchy. That's the non-informative, weakly informative prior for standard deviation parameters for the normal distribution or for whatever distribution, okay? Usually for normal distribution. So I have to know what sorry, I need to copy paste. I need to know the name of the parameter. And then I do the Cauchy. I do it the same for this one. And then now everything's complete. And then if you click, you have to make it sure that everything's correct again, right? And then you do this and everything's correct. Good. And then what you do now is actually, well, you call the STEM model from R and then you estimate it. Good. And then I will skip the estimating part because I have something else to tell you. Any questions? Yeah, sorry, you can't hear me. What I said. So suppose that we debugged everything and we call the model and we might receive some warning messages. So what I said is warning messages, they cannot be seen if we do not run it. You can only see the warning messages after you run it. So what we do now is basically, well, we feed the model to data and we see the results and we might get some warning messages. And actually, if you run this particular memory retention model, you will see a lot of warning messages. This is because, actually you will see this, you will have nearly all of the samples rejected. So all of the samples, they are divergent. They cannot really form a reliable estimation. And then if you do the pair plot, you will see all of the samples, they are, so in the literature, they are called pathological samples. So the samples, they're bad. You cannot really use the sample to draw further inference in your analysis. And if you zoom in a little bit, you will see actually, this is really bad, right? You cannot use the data. So good. And this is actually on purpose. So why am I choosing, why did I choose this particular example for the debugging? First of all, I created a lot of bugs and you have to fix it. And second, I will show you using this example that Stan doesn't always work. So in this particular case, if you plot the exponential part, so if this term, the calculation is above 1, the probability is 1, and then afterwards, there is an exponential decay. So what you learned from earlier mathematics, you are in school, is that at this point, you cannot calculate the differentiation, you cannot calculate the derivative, right? If you cannot calculate the derivative, then Stan won't work because Stan requires the calculation of derivatives. This is a little bit too technical, but don't worry, because you see the warnings a lot. And in this particular case, there are two possibilities to solve this. So one way is actually to write a if-else statement. That's the simplest way to solve this. So if this thing is above 1, and then say it's 1. If this thing is smaller than 1, it equals to itself. And then this one, you don't really require to calculate this smooth the curve because there's if-else. Second solution, you write your own function to try to smooth this part. If you make it smooth, then that could work, okay? But don't worry if you don't get what I said. If-else is the best solution, okay? Good. Yes, this is non-differentiable. Just basically means you cannot calculate the derivative. When Stan is trying to do that. Good. So in this particular example, I showed you what is a very bad fitting result. Very bad means there are a lot of divergence, and here the tree depth, and something like the Bayesian fraction information is also very low, and you cannot reliably trust your model estimation results. We know what bad estimation looks like, and we actually want to have good ones. So in this particular case, we have to know what we want to look for and what are the good model diagnostics that we want to keep in mind as a criteria when we were trying to evaluate the reliableness of the model. So there are quite a few criteria. For example, here, the number of effect samples divided by the total number of samples, this has to be reasonably large. And we know this one, this is very important. We have to know the R hats. The R hats, they have to be small, right? Small means close to 1. And then here also, it suggests 0 out of 4,000 iterations ended up with a divergence. Very good, no divergence. And then here means the tree depth is not hit by the sampler, so 10 is enough. And then this one, the Bayesian fraction information indicated no pathological modeling behavior. Good. So how you can get those lines, how you can get those messages, actually there is a function called standard score utility, and the function is to check the diagnostics of your model objects. And if you see all of them, you can go forward, luckily. So what we are looking for graphically or visually is that the chains, they will have to mix up. And in this particular case, they look very well. And another is to look at the pair graph. So I showed you previously here, they look very bad. And you see there are different small clusters, and the chains, they do not form a coherent bulk, the majority of the visits, the MCMC visits. Instead, what we would like to look for something like this is like clouds, and all of the chains, they are coherent and they look very nice, they look very smooth. And if we get this kind of result, we could, if in this case, we could trust our model sampling results. Good. Are there any questions? The last topic, well, this one, I can give you a very short introduction. So we do experiments and we measure data not only from, most of the time, not only from behavior, not only from button price. We might also record their brain imaging data, fMRI, EEG, or sometimes also eye tracking or physiological data, skin conductance, or this facial EMG, also physiological data. We are also interested in that part. So in this case, if we run a model, let's say the risk-Lavagna model, what are the hidden variables? The hidden variables, if you remember, we have the values calculated from the model, we have the prediction error also calculated from the model. If we have some other modalities of data collected at the same time, we could try to establish some connections between the hidden variables from the model and the other modalities of the participants, the data, the imaging data, brain data, or whatever data that you are interested in. And then this kind of analysis, it is termed as model-based analysis, because the analysis is based on the model, the computational model that we are interested in. Good. So this conceptual knowledge is enough, I think, and I don't really have to go too much detail. So we have the choice data, and we could calculate prediction error and value signal, and then we can see where in the brain is associated with the value calculation, in this case, the prefrontal cortex, ventral median prefrontal cortex, and then the prediction error, in this case, a little bit midbrain, the nucleic accumbens, okay? This is, if you do not know too much, don't worry, and there are papers you can read. The central idea is, I told you already, we have the model-derived variables, and we correlate that with other modalities of the data, in this case, the brain. Good. And then this one you can skip, doesn't matter. Okay, take a deep breath, and we will have the summary. So here I showed you earlier, and I didn't really explain to you, but I want to explain you now. So if we have the data, and we, first of all, we do not even have to have a model. We can do whatever behavioral common canonical behavioral analysis that we want, and we just calculate the accuracy, calculate reaction time, for example, here. And then later you realize, okay, maybe this is something that you would like to model, and then you do the model fitting. And model fitting, you do not fit the model to the data once, in the sense that you might have multiple models. You have 1, 2, and 3, and then you will use model comparison that we mentioned last week to decide which one is the best here, model selection. And we also mentioned posterior predictive check. So model comparison gives us relative model performance information, who is better, who is worse. But how good that is, we have no idea. So we have to use posterior predictive check to validate if the model is really a good model. So here, posterior predictive check. And then the checking part is to use the simulated data from the winning model and then compare if the simulated data, the pattern, matches the actual pattern from the observed data. And for more about posterior predictive check, there's a lot of papers, and I think I sent you earlier, or maybe in the syllabus. And there's something here inside. So here, well, when you were trying to come up with the model, well, how can you get all those models? You get from the literature, you get from your task, you have to imagine what task structure you have, what information you have shown to the participants. And this information, so all of them, they are recipes for building the models. And here, this is actually what I said today, right? You could, even before your data collection, simulate choices and then feed the model to the simulated choices to validate your choice of model. So basically to decide on which model you want to use. Good. So now we go to the summary. Looking back from the very first lecture, we did all online throughout the entire semester. So we started from the R and R student introduction. We spent quite some time on running the functions and to see how R works, writing loop, writing if-else, and try to plot. And then we moved down to the topics. Because we are doing Bayesian statistics, which actually relies heavily on probability theory. So we spent time talking about probability. Importantly to remember here is if the event is discrete, we call it probability mass function. If the event is continuous, we call it probability density functions. And there are two. One is the PDF probability density, the other one is the CDF, the cumulative density. We do not have events for only one, right? We do not have probabilities for only one event. We have probabilities for multiple events. So we have the conditional probability, the joint probability, the marginal probability, and then how to link that. Well, then there's the Bayesian equation, very famously. And we can actually derive the Bayesian equation always if we know the link between all those probabilities I had mentioned. And we want to know the probability of unknown parameters given the data we observe. So then we use the example of the globe tossing and then to catch, to see if water or land is gotten from under your right index finger, and 9 times of experiments, 6 times of water is the example that we carried through for at least 3 lectures. And we first started using a grid approximation, and then we switched to MCMC because I told you the denominator of the Bayesian equation here is useless, and we want to get rid of it by using a technique called Markov chain Monte Carlo. And then we revisited this example using MCMC, and then we move on to another example with multiple parameters, 2 in this case, for a regression, but actually 3, because you know there's not only the slope and the intercept, there's also the standard deviation of the normal distribution. And then we move on to the more interesting cognitive part. We were trying to introduce you the idea of cognitive modeling. Simply put, cognitive modeling or computational modeling is never a very new idea. Scientists have been using that for hundreds of years. In physics, for example, but in the field of psychology or cognitive neuroscience is a little bit newer, but it's already more than 2 decades, I think. So one of the most dominant model of all those computational models is the reinforcement learning framework. And we introduced you the simple Risk-Lavagna, and we started by feeding 1 participant, and then later we feed data from multiple participants. And we ended up with a hierarchical model, which takes the advantage of both the fixed fitting and also the random fitting. In essence, that means the individuals, they are supposed or assumed to be sampling, to be sampled from a upper level, group level distribution. So there is the group level distribution, the general one, the overarching distribution, and the individuals are sampling, they are sampled from the group level distribution. And then in this case, we also want to fit the hierarchical model, but we encountered problems, and then we optimized the model by reparameterize it. But actually there are multiple ways of optimizing, and go back to the slides. And then we fit not only one model, most of the case, we feed multiple models, and we have to do model comparison. Model comparison in essence means we have to balance the pure goodness of fit and model complexity. We would like to avoid overfitting. And the best way is to always do cross-validation, and it might take time and effort, and we use information criteria to approximate cross-validation. In this Bayesian framework, we use the WAIC or LUIC, the live and out information criteria, by using a package called LU, okay? So this is today, we talk about debugging, we got exercise, we see how to make it more practical, and then the very short introduction of model-based fMRI. So here is the summary of all those folders and exercises and the models, and if you're interested, so go back. And after the workshop, I hope that you are able to implement your own model. This is the highest standard. And if you cannot reach the highest standard, you should at least feel comfortable with reading mathematical equations. So for the second review paper, there are more equations, I think, than the first one. So don't get scared, and they are just equations. Actually, if you take your time, be patient, it's not so difficult to understand. Good. Yeah, this is fine. And always just practice makes perfect. And if you're really interested in the topic, and you can just get in touch with me, and I can tell you how you can go forward. Good. And this is basically kind of an interesting comic and joke in the sense that when you're writing the paper, so when you're working on your project, you spend most of the time working on your analysis and debugging, and actually not too much on the results. But when you are writing the paper, it's the inverse. You will have spent most of the part of your paper writing about this. And then the actual way how you did everything isn't supplementary. You don't really see that in the publication. All right. And all those models actually, so we think we thought Stan is not a really easy language to use in the first place, and we were trying to lower the barrier of using Stan. So a few years ago, we actually came up with a package. So basically, we code a lot of the common models in the field of learning and decision making into a package. So whenever your task is pretty much the same as what we have coded in the package, you can simply use it. You do not have to go through all those detailed procedures. But for educational purpose, what I show you is how you can do it from scratch. In reality, if you want to use it, there are packages. The packages actually has a lot of models, and it's growing. And another one is if you're interested in the topic of reinforcement learning and also in the field of social neuroscience, we recently got a accepted paper in SCAN. And I also like sharing everything online. So this is the GitHub page, the company GitHub page of the paper. Good. So suppose that you were now in the beginning of the semester, so you know maybe some part of the Bayesian, but some part of the Bayesian statistic you have no idea. And maybe in the middle of the semester, something get even blurred because you have get confused, maybe of the way I was explaining, or maybe just the topic's too complex. And even the topic you know previously gets a little bit vague again. So you really get confused when we were trying to covering the Bayesian statistics. What I hope is actually at the end of the semester, everything will become clearer, and you have an idea of how you can use Bayesian modeling in your own work and to do analysis. And this is basically to create a new way of thinking doing statistical analysis. Good. And if you want to go forward, before asking me, there are some summer schools, including the upcoming Mismatch online summer school. I got some of you. You got accepted. Congratulations. I also got accepted. I applied as a student as well. In the beginning, I applied as TA, teaching assistant, but I switched. But anyways, there are quite a lot of resources that you can utilize to boost your knowledge, to boost your skills online. References, no need, and acknowledgement. They are my former colleagues, and they really inspired me to do this kind of teaching, and I got my knowledge a lot from them. Any questions?